Hello guys, today in this video we are going to discuss about the reverse applied bias in a PN junction. So reverse applied bias in a PN diode. Okay, so when what will happen if you'll apply a potential between the P and N regions? Okay, so when we will apply a reverse bias, okay, between the P and N regions, then as we know, when some external excitation is given in the form of some voltage, okay, then the semiconductor will no longer be in equilibrium condition, right? So if you do this, for example, if we have, I mean, let me just show you the bulk model of PN junction. This is the metallurgical junction we said, and this is our P side, and this is the N region. And suppose the reverse applied bias, as we said, P will be connected to the negative terminal of the battery, and then the positive terminal of the battery will be connected to the N, right? So in this case, what will happen, right? This N region will, as it is connected to the positive terminal, okay, so it will behave like, a little more P type. Okay, like more P type means what? Electron will be like, tightly bound, because you can see it is connected to the positive terminal, so electrons are not provided with the extra energy, right? And same happens with the holes, right? Holes are connected to the this P region is connected to the negative terminal, so they're also um, not they will also not be diffused, right? Holes will not diffuse from P to N region, and electron will not diffuse from N to P region. Why this happens? As we know, the let us first do it in in the energy band diagram. So if I'll do it in terms of energy band diagram, what will happen, right? So the thermal equilibrium, in thermal equilibrium, when there was no EMF applied, right? No was applied to the PN junction, then you can see this was your X is equal to 0, and we said this is your plus XN, and this is your minus XP, right? So this here we said that the space charge region, okay, in the N you got electrons will move, so you got the positive space charge region over here and the negative space charge region over here, so you got a induced electric field this way, and this induced electric field actually prevents the further flow of holes, okay, from the P region to the N region, and similarly for electrons from N region to the P region, right? This is what we said. Now when we will connect it to a, like, a reverse potential, like, reverse applied bias will be given, then this, these electrons will be more, attracted towards the positive terminal, and similarly your holes will be attracted towards the negative terminal, and you can see the electric field that is induced here in the depletion region will increase, because your width of the depletion region will now increase, right? So width of the depletion region will now increase, so more you can see actually what will happen, that the what there will be no further flow of, like, the majority charge carriers from P to N region, right? So now in terms of energy band diagram, if you will see what will happen to the energy band diagram, let us just draw the P and N, the energy band diagram for P and N region separately, then we will see what will happen, right? Okay, for P region, if I'll just show you, like, this is suppose the conduction band, and here also you got the conduction band, because the same type of material, bulk material is the same, silicon or germanium, whatever you took. And then your valence band, okay, the energy the band gap is also the same, you can see that EV, right? And then here the Fermi energy level is somewhere in between. I will show you the Fermi energy level here. Suppose this is your Fermi energy level EFI, I am writing for intrinsic Fermi energy level. So same way here, this is the intrinsic Fermi energy level, which is somewhere in between EC and EV, right? Now this is a P region, so in P region we said that the Fermi energy level will be shifted towards the valence band, right? So the Fermi energy level, the position of the Fermi energy level here is this, okay, closer to the valence band, and let us name it as E, F and P. I'm writing, Okay, so Fermi energy level of P side. Similarly, here if you'll see, the Fermi energy level will be closer to the conduction band in case of N region, right? So this is our EF, the Fermi energy level of the N region, right? So this is what we got. And when we combined, we said when the P N junction were combined, P N junction was made, okay, when the P and N type material was combined, then we said the Fermi energy level will be constant throughout, okay, as you are considering the thermal equilibrium, right? So in that case, we said the there will be a drop in the potential, and we have already done all these things, right? In the previous video, you can refer to that. So you can see there is a potential drop here, okay, or the energy drop. So this is your EC, this is your EFI for both the sides, EC, and you got this EFI. And then we got the valence band, the same way. I will just show you the drop exactly up to the same length. Here I am not, okay, suppose this way I got the EV as well, okay. So this is your EV, fine, for both the regions. Now we said the Fermi energy level will be constant throughout as it is in thermal equilibrium. So here it has to be closer to the valence band. As you can see here, it is close to the valence band, and here it has to be closer to the conduction band. So we said the Fermi energy level will be constant, it will go like this. This is our Fermi energy level, which is maintained, which is kept constant, okay, which will remain constant throughout the P and N region, right? Now when you are applying, you see this P region is connected to the negative terminal and the N region is connected to the positive terminal. Then what will happen? Okay, so you are making P, okay, P region more negative, means more N type. So what will happen? More N type means this Fermi energy level of the P region will actually move upward, because it's getting, what, negative concentration, means more electrons will be supplied to this. So more electrons means what? The Fermi energy level, the average energy of the electrons will increase in this region, and hence the Fermi energy level will be shifted little upward, right? Okay, I mean, not exactly above the Fermi energy level, but it will move upward, right? The same way the Fermi energy level here will move in the downward direction, because you are making it more P type. I mean, connected to positive means what? Concentration of positive charges should increase, so the average energy of the electrons will drop, so it will go down this way, right? So by what amount you are giving? Suppose if suppose you are giving a potential of VR, right? So VR, if you are giving, then there will be a gap of, gap between these Fermi energy level should be a measure of the amount of potential. If I mean, potential you are giving, reverse potential you are giving. So in terms of energy, if I write, so the gap between this EFP and EFN will be exactly what? The amount of potential that you gave multiplied with E. So EVR will be the difference between this EFP and EFN. What way? EFP will go upward, closer towards, move towards the conduction band, and here EFN will move towards the valence band. So for the final structure we can do for the energy band diagram for the reverse applied bias this way. So what we will do is the conduction band, as it is, there will be a drop, there will be a little more drop, because the potential will now be what? The value of potential will be, initially it was, this value was only EVBI, okay, built-in potential barrier, but now it will further bend, okay, by an amount of EVR, right? VR is the applied reverse potential, right? So that can be written as EVBI plus VR. Okay, so this way you can write it. Similarly, this is your EC value. Now the intrinsic Fermi energy level, the same way you can see somewhere in between. So I will just draw the same amount of bending, and this is our EFI, the intrinsic Fermi energy level. This is just a reference point, it has no role actually right now. Okay, and then the valence band, we got the valence band as it is, somewhere here. The valence band will also follow the same, same amount of bending. You can see here, this is your EV, this side is P, and this side is N, right? Now, what about the Fermi energy level? As you are giving a potential of VR, or there is an energy drop of EVR between what? Between the FP and FN, right? So Fn, Fp is actually going up because you connected it to the negative terminal and you connected the N to the positive terminal. So you are making this more P type. So it's going down, Fn is going down and Fp is going up, right? So here you will see the position of the Fermi energy level here in the P region will be little up here, okay, and the Fermi energy level here will go little down. So now it is not constant, it is not constant. And the, you know, the gap between these two, okay, these two means what? This is your EFP, Fermi energy level for the P region, and Fermi energy level for the N region. Here will be that extra value of EVR, right? So here you got this EVR. So initially there was a bending of EBBI. Now additional, you know, reverse applied bias made additional bending of EVR, right? So now you can just write, like, you know, suppose I will write in terms of all energy. This is our E phi P. You can revisit to the previous video where we derived the built-in potential barrier, okay, in thermal equilibrium. So there we have already done these things, E phi, sorry, E phi P, and this is E phi Pn, okay, sorry, E phi Fn, let us write Fn, F for me and N for the electron N region, okay. Anyway, so now here you can see in terms of energy we can write. So what we got, the Fermi energy level will no longer be constant through the system as you are applying a reverse applied bias, okay. Fermi level on the N side will be now below the Fermi level of the P side. This is because of the reverse applied bias we said, right? So you are making the P region more negative and you are making the N region more positive. That's why there will be a shift of the Fermi energy level, right? And hence, if I write the total, like, you know, here we got this EVBI plus VR, this is the total bending. So if I write that E times VBI plus VR, this must be equal to what? E phi FP, okay, plus E phi Fn plus EVR. This is the total bending, right? So if you will take out, like, you know, all these E, then what do we got? We got this, you know, V total here actually, okay, is nothing but this phi AP, phi Fn and phi R. So V total here, okay, the potential difference that is created is equal to actually VBI plus VR, okay, which is nothing but your this phi AP plus phi Fn, right, plus the VR, the applied reverse bias, okay. So this is what we can write for a reverse applied bias. So the same way we can write all the other parameters, all the other physical quantities that we determined for the thermal equilibrium condition, okay. Only thing here will be what, initially whatever wherever we wrote VBI, now this VBI will be written as what, VBI plus VR for reverse applied bias. So that will be the only difference, right? So using this, if you want to write what is the space charge width, okay, what is the space charge width now in this case, you can see space charge width means what, the moment, you know, you can see there is a drop in the potential here, okay, the space charge region will be you know, this much, you know, here. If you want to write one expression for this, you just go back and see whatever potential, you know, sorry, the space charge width we determined for thermal equilibrium, wherever you see the, you know, the potential was VBI, now it will just become VBI plus VR. So that is the only difference. So no need to derive it once again, you can revisit to that particular video. So here we can write the space charge width, okay, for reverse applied bias in a PN diode, okay, can be written as, I'm just substituting the value of VVI plus VR in place of VBI only. So that can be written as twice of epsilon s, okay, so electric permittivity of the semiconductor, and then here it was VBI only, and now I'm writing it as VVI plus VR divided by E, and then you have Na plus Nd, okay, the acceptor and the donor impurity concentration, NaNd okay, this thing to the power 1 by 2. So this can be written as the total space charge width. Okay, so here you can see that this total space charge width, okay, increases as we increase the reverse applied bias. Okay, so you can see that W is actually proportional to this, this whole thing, like, PR to the power 1 by 2. There is a factor 1 by 2 here, but you can say that W is proportional to some to the power 1 by 2, so it increases. Okay, this can be confirmed from this equation. Okay, so in the next video for reverse applied bias, we can also find out the maximum electric field at the metallurgical junction. Okay,